I'll do this. So about a decade ago, Mark Minkalik and I started observing low-mass white dwarfs in the Sloan Digital Sky Survey. And what's new is that Gaia now provides us an independent means of testing that sample. So as you probably know, we called our survey the ELM survey because we were targeting extremely low-mass white dwarfs, things not seen in previous surveys. And to illustrate that point, this is the mass distribution of DA white dwarfs in the Gaia 100 parsec sample. And most white dwarfs have a mass of 0.6 solar mass or above, but the median mass of object in the ELM survey is at 0.18 solar masses, down where this plot goes to 0. So volume-limited samples are not always the best way to find interesting objects, certainly not objects in the tail of a distribution. So spectroscopically, these are DA white dwarfs. Physically, they are helium core objects. And as Ingrid said, they're interesting because you can't make them through single star evolution in the current age of the universe. Binary evolution is required. So our original approach for finding these objects was to select them by their colors in Sloan. And to illustrate, this is a color plot showing every star in Sloan with this particular set of colors. G minus R reflects temperature, and these cloud of dots here are stars with normal A-type spectra. So these are stars with spectra dominated by the hydrogen Balmer lines. U minus G color spans the Balmer decrement in the spectrum and reflects gravity at these temperatures. So the cloud of dots at the top are normal white dwarfs, stars with the same temperature but much higher gravities. And the low-mass white dwarfs fall in between. So these magenta lines show where theoretically you'd expect to find log G of 5, 6, or 7 white dwarf in this parameter space. And our approach was to observe, to get a spectra for stars in these color selection regions. It all started with my hypervelocity star survey targeting sort of light B-type stars, which by accident was a great way of finding low-mass white dwarfs. And then we intentionally extended this selection to cooler temperatures to really target the low-mass white dwarf objects. And it worked. Over the last decade, we've published 124 double white dwarf binaries now, all with orbital periods less than about a day. And yeah, and I guess what I've always wondered, though, is what we were missing with this color selection. And Gaia now provides us with an independent means of testing that. So these magenta tracks now are showing you where a low-mass white dwarf falls in the HR diagram, ranging from about 0.16 solar masses to 0.32 solar masses. And so this box is sort of the distinctive range of color and absolute magnitude for objects as seen by Gaia. And the combination of both color and parallax is even more powerful. Certainly as you go to fainter magnitudes, you're using 3 passbands. These foreground and background populations sort of balloon out and cover up the stars you care about, but the parallaxes remain good. And so you can cross-match these 2 selection techniques and really get a clean sampling. And so what we did is we expanded our color selection by 3 sigma color errors to really dive into these other stellar populations and observed only things that had parallaxes consistent with being a low-mass white dwarf. And our observational approach is clearly the same as always. We always get a spectrum of the object, fit it stellar atmosphere model, seen in red. If it's a low-mass white dwarf, we do time series spectroscopy. And these are single-line spectroscopic binaries, so what you measure directly is the orbital period and similar amplitude of the low-mass white dwarf itself. And this is an example of the J0651. So what do we find? That's weird. There we go. So of the 57 targets that satisfied our joint selection, this is what we found in sort of a temperature versus gravity. Blue dots are things we had already observed. Red dots are newly observed objects. We expanded our selection, so we have things at both higher and lower gravities than we care about. These magenta lines are the most recent ELM tracks from Alina Strawtree's 2016 work, ranging from the lowest to the highest mass tracks in her models. And I guess I should point out the solid dots here are ones with full radial velocity orbital solutions. And so this sort of cyan box here is what we would call sort of a clean cut of this sample, right? This is our clean ELM sample. Objects for parameter space for which we have a complete set of observations and which sort of optimally matches, overlaps between the data and the models. So in total, we found 17 new white dwarf binaries with our sort of follow-up observations, 9 of which fall in this sort of clean elm region, which implied that our original color selection was about 90% complete in Sloan. So now that we've cleaned it up, we can revisit some of our previous conclusions. Turns out the conclusions don't change very much. But so this sort of shows our whole sample of low-mass white dwarf binaries, where I'm plotting here the mass of the white dwarf we observed versus the orbital period of the binary. So orbital period is not a parameter we selected upon, so we can fairly test this. Our clean objects is sort of basically things below about 0.3 solar masses. That's sort of parameter space for which we should be complete in magnitude and our color range. And one thing that's interesting with Gaia 2 is you have proper motions. So we've combined our rate of velocities with the Gaia proper motions to measure the 3D motions of the white dwarfs and assign them, sort of classify them by their motions. So the blue dots here are things that are consistent with being disk-like objects, and the red dots are things that have halo kinematics. Lee et al. Have pointed out a while ago that there's an interesting correlation between the mass of the lowest mass object here and their period, and that's the signature of what you'd expect from a Roche lobe formation channel, where the mass of the white dwarf correlates with the period of the binary. But we also see an interesting batch of objects here at slightly higher masses that are only found at short periods, or periods of less than about an hour. And those very likely probably come out of the common envelope formation channel. So once formed, all of these binaries will, merge due to gravitational wave radiation. And the merger time scale for the shortest period systems is about 1 million year, right? These are merging quickly. What they turn into is an interesting question. It depends whether they turn into a unstable or stable mass transfer binary. Depends primarily on the mass ratio of the system. And so I'm plotting here again is now the mass of the observed low mass white dwarf versus the constraints on the unseen secondary, which is always the accretor in our systems. Because we don't measure the mass of the secondary in most cases, these dots sort of represent Monte Carlo draws from our clean sample, given the measurements, the errors, and any inclination constraint we have on that object. So in some cases, we have eclipses or ellipsoidal variation or other, some inclination constraints. The solid lines here come from Tom Marsh's 2004 work. So the blue lines and the red lines, these are sort of the mass stability boundaries, right? So 1-to-1 mass ratios will always turn into unstable mass transfer binaries. Things beyond a 1-to-4 mass ratio should always turn into a stable mass transfer system. So these objects will very likely become AMCVN someday. But the vast majority of the binaries we observe merging today fall in this ambiguous region in between the solid lines. And so to understand what they will turn into actually requires additional information. In previous talks, I've discussed how we can use the merger rates that we observe as a constraint on what these things will turn into. But the future holds a different constraint, which is a direct, well, not direct measurement, but a direct constraint on the mass of the unseen secondary. So that's weird. There we go. So NASA and LISA are building, ESA and NASA are building the LISA milliHz gravitational wave observatory, which will detect, 10,000 or more double white dwarf binaries in our Milky Way. And we already know about some of them. So this plot shows you the characteristic strain versus the gravitational wave frequency for all the white dwarf binaries in our Helm survey. Most of the objects on this block line is the 4-year LISA sensitivity curve. So most objects fall below the sensitivity curve. They just sort of will contribute to the overall foreground glow of all the binaries in the Milky Way at millihertz frequencies. But about 8 objects sit far enough above the curve that LISA should individually resolve them. And that gets interesting. I should point out, too, that Kevin Burge and others found other double white dwarf systems up in this region, and many AMCVNs are also in this region of parameter space as well. And LISA will detect them all. Our 12-minute period system, J0651, is still one of the best detached binaries, though. And the gravitational wave community loves calling our object verification binaries, but really our light-based measurements are critical for understanding these objects. So LISA will only localize these binaries to maybe a square degree on the sky. So simply knowing the location of a binary is additional information that Shaw and Elleman have shown that will can improve your gravitational wave solution by a factor of 2. Moreover, LISA, most of these binaries will appear as constant frequency sources to LISA. Like LISA won't be able to resolve the orbital frequency change during its mission lifetime. And so Shaw and Elleman have shown that if you have additional inclination and period change measurements, such as from optical eclipse timing, that can improve the gravitational wave parameters by a factor of 40. So the combination of our light-based measurements and the future gravitational wave measurements means that these systems are really very interesting for doing future work. So until LISA happens, however, the only really link between our current observations and what the future gravitational wave measurements might be are binary population models. So this is a plot I've taken from Lamberts et al. And it's a kind of a view of the sky as LISA might see it. This is plotted in RH space, and these ellipses are sort of the 1 sigma positional constraints for a model binary population of double white dwarfs in the Milky Way. And so you can think of this as sort of a guide to how and where we should look for these future multi-messenger systems. And I'll end by just by saying that our observations provide a way to anchor these models with real numbers. Experimentally, there's no way we can ever observe all these systems, right? So I think the best approach is just to have complete and well-defined samples. And I'd love to understand what our ELM sample could do with this. Thank you.
Thanks, Warren. Can you say a little bit about the part you skipped over, what the merger rates do tell us, what the inferred merger rate do tell us?
Yeah, I don't have the slides here, but so we have a managed and limited sample, and you can back out sort of a merger rate. And the short answer is that the objects we see merging have a rate that's something like 30 to 50 times larger than the formation rate of AMCDNs. So our objects can't not alternate AMCDNs, otherwise there'd be too many. But they do match almost identically what you'd expect for the arc or Bohr formation rate. So it's all factors of few kind of uncertainty, but it would appear that most of the objects just kind of come together. And you pointed this out as well in your own paper.
So for the ones that do form disks, if you just constrain yourself to those, does that merger rate surpass the AMCDN birth rate?
No, it's about right, actually, because that's not the right plot to show. But it turns out it's sort of only a small fraction of our objects would, certainly turn into sort of AMCDNs. And so it's actually about the right rate. You're down by an order of magnitude easily. And so it's actually, given the uncertainties, it's plausible. Thanks.
Other questions, comments?
Back a bit, you had a mass plot.
Like that one?
The next, yes. There's an interesting overdensity there. What's that all about?
Oh, you mean this blob?
Yes.
That's J0651. It's an eclipsing.
It's what?
This is J0651, the eclipsing double white dwarf binary. So, right, there's some mass ratio. We only observed one. It's a single line spectroscopic binary for which we have an inclination. So there's some error on exactly what the exact masses are, but we have a good mass ratio constraint. So it makes that sort of dot pattern in this plot.
I was hoping for something more interesting.
Yeah, and you can't see it because it's all blurry. But there's I don't know what JJ knows the numbers. There's maybe a dozen objects with elliptical variation. We have inclination constraints for some, and Makama pointed out some of the more massive objects, from the single line spectroscopic binary that the companion has to be a solar mass or above. And so those are the ones we targeted with the radio and X-ray observations. And there's nothing there. So I don't think they're pulsars.
Okay, I have a question maybe. You can go to the next, I think it's the next slide.
This one?
No, the previous one, sorry. That one. All those green points, they are above, the mass is above 0.3 solar masses.
The green, why does it do that? The green points are like these objects here. So things that are higher log G, but we didn't follow these up in a systematic way, and we weren't really targeting them. So we did find objects that are log G of 7.5, right?
Okay, but
so-
do you know if some of them fall in the instability strip of low masses?
Pulsations? Yeah.
Yes.
No, those are the pulsators that JJ found.
Oh, okay.
Yeah.
Because if you have binary parameters and the pulsations, you can do a double restriction of the composition of the star, for instance. So, okay,
Yeah.
thank you.
So I think a half dozen are confirmed pulsators. Yeah, the DAB strip sort of just continues down and log to your mass, however you want to think about it, into this regime.
Looking at this plot, I'm staring at the lowest mass white dwarfs you have in this sample. It looks like they're around 0.16.
Yeah.
And they are preferentially disk. Do you think that's meaningful yet? I'm just doing blue versus red from my distance here.
Yeah, I think the shortest period systems are mostly disk, so I think that's probably meaningful. But overall, the distribution, I've tested it, and given the uncertainties, in this parameter space, you can't distinguish anything.
Yeah, so I'm doing a mass cut. So
Yeah,
I'm saying
yeah.
if I go below 0.16, I see about 8 points, and they're distributed in mass. They're everywhere in orbital period. Pardon me.
Yeah.
Right. So you've got a lot of diversity of orbital period for the low mass.
Yeah, that's these things over here, right?
Yeah, I can't read. What's the?
This is the
mass?
0.16 holo mass
That's the
track
0.16.
here.
Thank you. Okay.
And you can see that the data doesn't overlap the models perfectly, so this is interpolating exactly what masses they are. We measure the temperature and gravity based on them, but we we derive the mass from the mass rate isolation, right?
Right, the colors on this plot mean what?
Sorry, the colors are different in this plot, so I apologize. So I'm mixing and matching plots.
Okay.
In this plot, the blue dots are ones we'd already observed.
Got it. Okay. Thank you.
So you have about half as many, or you have about the same number in the disk and the halo, I think?
No, about a third are halo, roughly speaking.
Or is that, to what extent is that driven by looking in that Sloan footprint versus?
Yeah, I don't know. So, we observed in Sloan, which is essentially everything above latitude 30, roughly, right? So, we were looking at a high latitude region, but the median distance to these objects is about a kiloparsec. We went from 15th to 20th magnitude. That was our magnitude range. And so most are faint magnitudes. So the typical distance was about a kiloparsec away. So they're not that far above the disk. So it's not a surprise we're missing thin disk objects, but yeah, whether it's a third halo makes sense, I'm not sure. That's just kinematically what they look like. They're moving hundreds of kilometers per second.
Right, yeah, it'd be interesting to model if it's somehow driven by age or metallicity.
I don't think there's any age constraint here that I would believe anyway.
Any further questions? I just want to comment. So when I was studying my PhD, LISA was meant to be launched in 2013. That didn't happen. And then so recently I heard it was 2034, and then I heard again 2037. Is that like roughly the projected launch date of LISA, as far as you know?
The European Space Agency is leading the mission, and so
Yeah.
they've committed to it, but they have a funding line issue with Athena, so they're
okay.
currently reviewing both mission concepts. I think with explicit desire to downscope Athena to a more manageable budget level, but how that impacts LISA is unclear.
Okay.
But yeah, nominally it's mid-2030s launch, which means the data probably won't be out till later.
Yeah. Okay, thanks. Let's thank our speaker.